I'm Tim Mooney, and I'm going to be talking about EPICS records. And this lecture is mostly for people who want to write EPICS databases. So the first thing is, where do EPICS records come from? Most of the records that you use are in EPICS base. There's a number of records that implement the basic data types that are used in writing databases. I'll be going through a whole list of records from base and elsewhere in a little bit. But the general purpose record types are in base, and they're documented in the record reference manual, which I think I have a link, and you can probably figure out how to get to that. They don't have any displays or databases or examples or anything like that in base. Base is mostly just the code. You can also get records from record types from the EPICS collaboration. There are some general purpose and some application-specific record types. And some of them are supported for use by collaborators, and some of them you're kind of on your own. And some of them come with MEDM displays or CAQTDM displays specific to that record type, and and there are a lot of examples of databases with record types. And you can write custom record types. Now, I'm not going to be talking about that today, but it is something that EPICS supports. So the record reference manual is basically the core material for this course, and you can just read that thing through. I think that's a good thing to do. There's a link to get you to it. It's a wiki, so if you find something that you don't think is right, you can change it. I hope you know what you're doing if you do that, or you check with somebody. But contributions from users and developers are welcome. And what's in it? First of all, it has a good discussion of database concepts about how things work, and a lot of the things that you guys have already heard from Andrew in earlier lectures. It has a list of the fields that are common to all record types, and these are the fields by which EPICS manipulates records and causes them to process and checks on who is looking at them, who's monitoring their fields, and all that. And there are fields common to many records, such as, for example, the n-log and binary and string and long out records I'll talk about later are in EPICS space. They all have a set of fields in common, and so you can get some of this stuff. You don't have to look at every single record in order to get some of this stuff. And then there is the documentation of the record types themselves. So it's just a list of them, and you can look at all of them. So when do you use that? I would skim through it before writing any databases, and I would read through it cover to cover before writing any records. And otherwise, it's just a reference. There are other ways to get the information that's in the record reference manual. So the manual outline, as I said, it begins with a discussion of concepts, and you'll notice fairly quickly that there is sort of special definitions of a couple of words here that are used in EPICS differently than in common practice. The words scan and process both basically mean execute. An address can either be the name of an EPICS PV, or it can be actual specification of how to talk to something in hardware. A link is a special EPICS thing for writing to hardware or to other EPICS PVs. And monitor is the process of telling everybody when something has changed. You'll also see the word post. So if you write to a field and run a running IOC, anybody who is monitoring that field will be notified that you wrote that value. It's not the record's responsibility in most cases to do that. That's what monitor means. So then the rest of the manual is the record reference, and as I said, there might be some stuff that's out of date or a little bit inaccurate. Your help is appreciated. If you're not going to fix it, let somebody know. That'd be nice. And it has a lot of tables like this, so I probably should just go through this. The first column is just the field name, and then the second column is the description for humans of what that field name actually means. So EGU is engineering units, and then there is the C code type, or the EPICS type of that field. In this case, it's a 16-byte string. DCT means database configuration tool, and this column tells you whether or not you're allowed or whether or not it's supported for you to set that value in a database. Can you initialize it before running the database, or do you have to write to it afterwards? Then the next one is the initial value, which in most cases is going to be 0. Access means, can you read this field? Are you allowed to read this field? And in most cases, the answer is going to be yes. Modify you may or may not be able to modify. You can't change the record's name, for example. And there are a lot of other fields that you won't be able to modify. And this column is, it's not really obvious what this column means. This is, will the record ever post a monitor on that field? So you probably know that monitors are almost never posted unless a field's value has changed. So if a record doesn't change a field's value, it's not going to be posting. It's not going to be monitoring it. But this will tell you if the record does itself make a change to that field, will it post it? And the last column is actually, I think, the most important here, and that is, if you write to this field with a CA put, will the record process? You probably know there's two ways to write to a record. You can do a database link or a link that has an NPP or a PP on it. You guys have heard this already, right? And for those, you get to choose. So this column doesn't apply to that kind of a link. But if you're writing it over channel access, then you need to be aware of the setting of this, because some fields you write to will cause the records to process and some fields won't. And you're going to want to know. And there's one other little glitch. If you're writing from one record to another record in a different IOC, all links are going to be channel access links, because channel access is what bridges the gap between IOCs, right? So even though it may look to you like you're doing a database put, you still want to know the value of this field. So collaboration supported records, there are a bunch of them, and there's a list of them, the soft support list in the main EPICS site. And you can also get information about these from the Tech Talk email list, although you're not going to ask EPICS Tech Talk what record types exist. Normally you would say, here's what I'm trying to do, how do I do it? Is there a record type that's particularly helpful in this kind of an application? So the soft support list contains entries like this. There's an enhanced PID loop record. The gen sub record actually is not used anymore because there's an A sub record in EPICS. There's a number of records written just by, just guys. And then there's a link to the documentation and the source code and all that you can get. A record is actually defined in a DBD, a database definition file. And there's a record name, and there's a list of all the fields, and then there are attributes for all the fields. And you can look at that file. If you've built an IOC, there will be a DBD directory at top level. And you can go right in there and you can look at that, and you will see definitions of all the records and all the other things, device types. Okay, so here's basic input records. Actually, there's 2 pages of this, basic input records. All right, so there's an analog input, there's a floating point, double precision floating point value, there's an array of those things. These are all inputs now. Binary, which really means Boolean, true or false. And there's a multi-bit binary, which, if you're talking to hardware, is a bit pattern. If you're not talking to hardware, or from the user's viewpoint, that's just a menu, right? That's just a list of the bit patterns you might write. It's an enumerated type, essentially. And there's a multi-bit binary direct, which is the same as a multi-bit binary, but it also allows each bit of that to be brought out as a separate field. And there's a string in record, which is limited to 40 characters. There'll be a longer one in EPICS 3.15. There's a long in, and by that is meant a 32-bit integer. A waveform, which is an array of types to be defined in the database. The waveform you can have an array of characters, an array of strings, or array of longs, or whatever. And that's only an input. There's no output record for this type. And then there are specialized records. A multi-channel analyzer is technically an input record because you're reading from actual multi-channel analyzer hardware. And similarly for the scaler. So those are, they're input records, but they're specific. And those are the first 2 records that are not, I guess there's another record that's not in base. No, those are the first 2 records that are not in base. A lot of the records I'm going to talk about come out of Synapse package, which is an add-on. So there's a bunch of algorithms / control records. The original record for this purpose was the Calc record. It's rarely used anymore, except in existing databases. Most people use the Calc out record instead because it's better. It's got more features and more options. And it has the same, expressions are the same between these two. So you can have an expression which is 0, and the result is 0. You have an expression A, and the Calc record has an A field, and so this will grab the value from that field, and the expression will have that value. It also has a B field, so you could add the two. You could take the sine of A times degrees to radians. You know. So those are the kinds of expressions that you can write into a calc record or a calc out record. The calc out record is different from calc in that it has a conditional output link, which is really useful in databases, in writing databases. So you can say, I only want the output link to fire and write the calculated value if it meets some criteria. And the criteria is expressed in the form of an expression, a calc expression. And then there are output link options. You can say every time, which means no matter what, write this value. Or you can say only if the value has changed or only when it's 0. And there is also a separate calc expression. So that you can say when the normal calc expression returns a 0, then you can have it execute the other calculation expression to get that value to actually be written. So the calc out is quite a powerful record. There are variants on the calc out record. These are in Synapse. scalc out is the same thing except for strings. You can do string expressions, and it has string fields. So in addition to A through L, which are double precision fields, there are AA through LL, and those are string values. And it's got, as you would expect, there are some different operators and functions that you can call from the string calc out record. And the transform also uses the same calculation engine as the string calc out record. So you can have those same kinds of expressions. And it's kind of like 16 calc out records, sort of pasted one on top of the other, in which each one is executed in a certain order. The compressed record, I think, is not that often used. It has a couple of different uses. One, it can collect a bunch of values and produce the median or the average or something like that. It can also collect a bunch of values and then just collect the first n values of some PV. So if you want to convert a series of scalar values into an array, you can do it with a compressed record. Similarly, the histogram record is rarely used, and it does exactly what it says. It accumulates a histogram of scalar values. The subarray record is intended to grab a piece of a different array record. So you tell it which array record, you tell it which offset. So I want elements 10 through 20 from this array. The A sub record this is very powerful. You write a subroutine to actually define what the record does. So it's kind of like writing your own record type, but you don't have to write the fields, and you don't have to do all the EPICS stuff. You just have to define the algorithm that you want this record actually to execute in response to changes in its fields. And the array subroutine is particularly useful because the fields can be of any type. You can have some double precision fields and some string fields, and a lot of different, for both the inputs and the outputs. And the outputs can also be arrays, or the inputs can be arrays as well. A D fan out, the purpose of this record is to take a single double precision value and write it to many fields, to many other PVs. And the fan out is similar, but all it does is execute. I don't use the fan out record anymore because I almost always can just use the D fan out for the same purpose, and I don't have to learn two records. The select record is for, you can link to many PVs, and then there's an algorithm which you tell the record which of those PVs you want the value from. And the sequence record has sort of the same kind of selection methodology as the select record, but its purpose is to write things. So it can write up to 10 output value links, and there's a mass. You can say write everything, then they'll be written in order, or you can say only write this particular one, or you can say only write these particular ones. And each one of those causes execution. So the sequence record will go step by step through this execution. And there is a variant on that record, the sseq, which is pretty similar, but it can also operate on strings. The seq record only operates on numbers. The string sequence record can operate on strings or numeric data, and it also has an option of waiting for completion after it's written the value, and assuming that the value has caused some processing. Which is a pretty handy thing, because if you want to do a sequence of operations and you want to make sure that the first operation is done before the second operation starts, With the sequence record, you can put a delay in there, but you're not guaranteed that the second operation won't start until after the first operation is finished. So the string sequence record addresses that kind of a need. And the scan record is it's fairly complicated. It's got a number of PVs that it writes to set conditions, and then it will trigger some kind of a detector, and then it's got a number of PVs that are used to read values from that detector. And the idea is that you'll set conditions, trigger detector, read values, and do that sequentially. And that's what experimentalists normally mean when they say scan. So that's why the record is named that. It also has connection to a data storage client, so it writes the data after the scan. I'll talk about this later next year in talks more about beamline controls and Synapse. There's a subroutine record, which I probably should have discussed before the A-sub record. The subroutine has got basic 12 input lengths, and it has a subroutine, and it produces a result. And you get to write the subroutine and link it to that record. The record doesn't actually do anything like the A-sub record. It doesn't have output links in that. It just calculates a value. So there are some other records that are, I would say, less commonly used. There's an event record that can post a soft event. I know Andrew talked about this earlier. You can post an event, and then any other record that has told EPICS that it wants to be processed when that event occurs, all of those records will be processed. You don't have to have direct links to those records. You can just say, read event, and then everybody who is subscribed to that event will do whatever is supposed to happen at the read event. The EPID record is for proportional integral derivative control loops. It's a fairly specialized record, and I don't think I can get into enough of the details to make it worthwhile. The permissive record I actually don't know anything about. I've never used it. And I also have never used the state record. But it's clear somebody wrote these for client-server communication, for communication between a client and a server. So if that's something that you need to do and the other available records don't seem suitable, you might want to look at that. So output records now. There's an output record to correspond to most of the input records I already talked about, so I probably don't need to discuss these very much. But I do want to say one thing. If you're using a value in a record that's just going to be, say, part of some calculation, you're just using a record to hold a value, I would use an output record rather than an input record. I think that's generally, and partly it's because output records have an output link. They can write something. And they also have an input link, whereas the input records only have an input link and are a little bit less flexible. So these directly correspond with the records we already talked about. Outputs for arrays, for Boolean values, for long values, multi-bit, multi-bit direct, and then sort of ancillary. The motor record's technically an output record, right, because it writes to hardware. But this is worth a whole lecture all by itself. I'm not going to go into the details of the motor record, except that it controls stepper and servo motors. And it there's maybe 30 or 40 different kinds of motor controllers that are supported for this record type. The string out is similar to the other basic type records that write outputs. It writes as character string out. And then there are a lot of specialized records that you probably won't use unless you're working with the folks who wrote them. They are that specialized, I think. I don't know really anything about these records. Have you used these records? Okay. So if you're doing RF amplitude measurements, it might be a good idea for you to talk to the guy who wrote this record. But that's not a really mainstream thing. So which record is right for soft parameters entered by an operator? Well, I already said, I kind of gave it away already, didn't I? The analog output, I think, is best for that. MBBO is good for that. Normally, you don't use input records for that. For multiple output actions, my favorites are the sequence records and their variants and the fan-out record. If you want to choose an action based on an operator selection, you can do this with the Calc out record, because as I said, its output link is conditional, and you can set the conditions yourself at runtime. And an MBBO also has a way of selecting one of its input values, or a value to write to. So I'm starting to get toward your question here. How does an IOC find out what record types exist? Everything about record types and the device support that goes along with them, and any menus that are required by fields in the record type, and other configurations. They're all defined in what's called a database definition file, and those all end in .dbd. So the IOC build, when you actually run make, it builds a DBD file that contains everything. And you can look at that. It's really long, and it's not that interesting, but there's a lot of good information in there. And this is what database configuration tools will look at when they want to know what's the default value for the sdis field or the disv value for this particular rate. It'll look there and it'll see it, right? This file is loaded by the IOC when it starts up, and this is really where all the information about which record types are going to be available to this IOC. So how does an IOC know about record instances? You might have a couple of analog output records, right? There's an analog output record type, which is in here, and then there are a whole bunch of instances of analog output records that are in use in databases, and you'll find those in database files, and you write these things that you load. So during the IOC boot, one or more, or maybe tens or hundreds of database files will be loaded. And the database files define the record instances, but they don't have to define anything that's already been defined about the record in the database definition file. So in particular, all of the default values don't have to define those because they're already in the DBD file. There'll be one record instance, record type defined in the database definition file, and you can have as many instances of that, including 0. If you don't define any instances of that record in the database file, then it exists in theory, but not in practice. So here's a database definition file, the first little bit of one. We haven't gotten to any records here, but there are menus, and you can define, for an AI record, this IOC is going to have this particular device, which you can specify by saying raw soft channel, and here's the routine that's actually going to run. So the DBD also defines the device support and the drivers that have been added to be used by these record types. This is part of a file. This is a very small part of a DBD file. And there's no records in here yet, right? This is just the menus that will be used by some of the fields of some of the records, and the devices that might pertain to one particular record, and the drivers that actually are not associated with any record. It's like, yeah, you can look at part of this as sort of a header file for EPICS to read, right? Because when EPICS sees this, it will look for DRV VXI, and it'll find that symbol in the compiled code, and it's a callable thing with a set of arguments that are standard for drivers, right? So this is just a list of all of those things that EPICS can expect to be able to find in the executable file. So moving on, later in that file, here we get our first record type. So this is the definition of an analog input record. And remember I was talking about fields common to all records? Every record, in order to be an EPICS record, has to have this in it, and it contains all of the fields that EPICS needs to be able to manipulate that record. The scan field, for example. All records have to have a scan field. All records also have to have a val field, but that's not in DB common. You are allowed to change the type of the val, right? But you still have to have a val field. A lot of records have output links. There might be menu valued fields, doubles, shorts. So whoever wrote the record is the person who defined all of this stuff. So now a database file, you don't have to define the record types, so you can just say record. And if the BO record hasn't been defined in the DBD file, it's not going to work. Right? Somebody else has defined the BO record, and all you have to do is say, I want all the default values of the fields except for these fields, and here's the values I want for those fields. That's the way a database works, if you're typing it in a text editor. If you're using a database configuration tool, there will be another way for you to specify the values of fields. So there's a binary output record, there's a calc record with a couple of non-default values. Here are some more of the values that you can set for an AO record, for a Calc record. In most of the databases that I see, there's just not very many non-default fields for a lot of records. So how do you load all this stuff into the IOC? There are two commands that you need to know about. dbload database, typically there's only one of these, although you can actually have more than one. But typically there's one of these that loads everything, which defines all the record types, all the device support types, and the drivers, and the menus, and everything for this IOC. And then there will be several, and maybe several tens of calls of this kind, dbload records, which will load the databases that you or someone else has written. And this is what the IOC is actually going to do. And then after everything's been loaded, then you tell EPICS that you're done loading it, and that it should start initializing all that stuff. And it should go through all those records and make sure that if they have any links, those links get hooked up, make sure that all the initial values get set in the event those were specified. So one or more database definitions files has to be loaded first. And you notice that you can specify values here so that you can load more than one copy of this database. And you can say, well, for this copy, I want this internal macro, it's called, user, to be student 1, and then you might load it again with another one, student 2. And then there will be two complete sets of the records that are in that database in your IOC, and they'll all be identified by different names. And this is really handy because you almost never write a database unless you're going to use it over and over again, unless you're going to have multiple copies of it. And then, as I said, the IOC init command starts database processing. So how do you write database files? I usually write them with a text editor. But I've also used GDCT, which I don't think you can even use anymore. And I've used VDCT, and that's pretty handy. I haven't tried TDCT. You can write them with a script, and that's actually fairly common. If you have, it's pretty common for the machine because they've got 80 different instances of a magnet, and they all just differ in very slight ways. They're all the same kind of magnet. A lot of their database will be written by a script. You can pull information out of a relational database, and anything that you can do with a text file, you can write a text file in many different ways, right? The difference is, in these three cases, it's your job to figure out what values are legal. If there's a menu, for example, what are the available choices for that menu? And so you might look at the record reference manual, or you might look at the DVD file and see what are legal values. If you're using the database configuration tool, it will do that for you. And it will do that by looking at the DVD file, as I mentioned earlier. And VDCT, I don't know about TDCT, but VDCT is actually hierarchical. You can, it can develop very complex databases. A couple of fragments that you might find in a database. What is this database doing? This guy's not doing anything, right? It's scanned, it's passive, it's got a value, it's just sitting there holding that value. This guy is scanned once a second, and it's going to grab two numbers, and it's going to subtract one from the other, right? And its input link, this input A, the links will be fired or executed in order. And input A will be done first, then input B, right? So input A is just going to, it's NPP, so it's not going to process the record. It's just going to grab the current value. And then, immediately afterward, input B is going to process the record and then get the value after the record is finished processing. So these values might be different. This will get the value from the last time the record was told to process. If this record is never told to process in any other way, then the next time the record runs, its input A field will get the value that resulted from the previous input B's links processing, right? So in other words, this is going to calculate the rate of change per second of this input value. Usually that's what's going to happen. You guys have talked about synchronous and asynchronous records, right? So if this record is synchronous, then that's what's going to happen, because when you tell it to process, it processes immediately, and the value that you get back from that input link is going to be the new value. But if this is an asynchronous record, that's not what's going to happen. This guy's going to tell it to process, and it's going to spin off a command, basically, to do something, and it's going to return immediately with the old value. And then the next time you process it, you'll probably find that value. And that's one of the reasons why people say that EPICS is best driven from behind. It's better to put stuff than it is to grab stuff, right? Because of this, because you don't really want to be thinking about whether or not this is an asynchronous record. You might not know. You might not be able to tell. So anyway, but that's basically how links work and the difference between MPP and PP. So how about this guy? I actually have never used simulation mode. So when I was going over this thing, I learned it, I guess, for the 4th or 5th time, but I actually still haven't used it. But anyway, what's going on here is this simulation, SIML field, this goes and grabs for this record whether or not we're in simulation mode. So both of these records are pointing at the same value to find out whether or not they're in simulation mode, which is pretty handy, because if you want to put a whole machine into simulation mode, you don't want to be clicking on each record to do it, right? So there's one value that tells all the records in this database to be in simulation mode, and then their behavior changes. In particular, the output record doesn't write to hardware when it's in simulation mode. And the readback isn't going to be reading from hardware when it's in simulation mode, but yet it has to get a value. So what this guy does is it grabs the value from the output record and pretends that it read it from hardware. So that's what simulation mode is good for. So you also know that records have alarms, and that alarms can be propagated from one record to another. So that if a record that's very low down in the database has a problem, records that are intended to sort of accumulate information higher up in the database, they can find out that there was a problem in records that they were linked to, because alarm information is propagated through links. So, and that's what this second attribute here, MS, maximize severity. The default value is don't maximize severity. So when you maximize severity, it takes the highest severity value, the most serious problem. And this record, if it's got some other reason for being in alarm, it will take the severity. If this severity is higher, it will take that for its own severity. And that way, alarms can propagate up, and you only have to look at the top. You don't have to look at every single record to find out what went wrong. So what's going on here? This guy's getting scanned. Nobody else is getting scanned. So everything is going to start from here. Every 5 seconds, this guy is going to be told to process. But it can also be told to process by this guy. Right, so this thing is going to be, effectively, it's going to be periodically scanned. But if a record's periodically scanned, you can't tell it to scan, right? You can't tell it to process, because it will only process every 5 seconds during that period. So if you want this record to be able to process periodically, but you also want to be able to tell it to process yourself, then you use this kind of construction. Oh, and here's another little handy little thing. If you don't want this record to process, you can set its scan disable link to some number, and then set the disable value to that number, and then it won't process. I mean, you can tell it to process, but the first thing EPICS will do is notice that it has a scan disable link. It'll grab the value from that link, and it'll compare it to the dis-A field, or to the dis-V field, and if those things are equal, then it won't process the record. So that's pretty handy. So remember earlier I said this, you could have a sequence record execute not either all or a selected subset of its fields. And the way you do that is with this select mode. In this case, you set the select mode to mask, and that says I'm going to get a integer value, and I'm going to use the bits of that value to tell me which of the sequence records fields should execute. And I'm going to get that mask from this select link. which is this field here. So it can either be the binary number 3, which means links 1 and 2, or 0 and 1 and 2, or it can be FF, which all of them, 5, which is, so it's the binary pattern that determines what happens here. Among the fields that are in DB Common that I told you about earlier is the mlist field, and that's what EPICS uses to keep track of who's listening to this record. So you can look at this mlist field, and you can see whether or not, if nobody is listening to this field, then you can process. As a result of that, you can find out if anybody is listening. And in this case, what they did was they put an invisible widget on a display. So whenever the display is called up, then there will be a monitor on the field that widget is connected to. So you can tell if somebody's looking at it. One of the things you can do with standard records like AI and Calc and all is sort of prototype something that you're trying to figure out how to do, how to support. This happens quite a lot in Beamline software. A lot of database development actually happens at runtime. If you're implemented, in this case it's a BPM record where you're going to have inputs for 4 leaves of a beam position monitor, then you can do a calculation to add them all to get the total intensity, to subtract them to find out how much is left and right, that kind of thing. And so you can do this kind of thing instead of writing a BPM record, or to prepare you for writing a BPM record.